So I think it's about that time. It's 3:30, so we'll go ahead and get started. I would like to welcome you to this session, tutorial session on graph-based modeling, control, and optimization for multi-domain and multi-timescale energy systems. This is a collaborative effort, and you can see many of the folks there. It's not just multiple people, it's multiple institutions, which is awfully nice to see. This is the order in which they'll be going roughly, except Joe, I know you're actually a little bit downstream towards the end as well too. And so this has some background on the modeling. There's also going to be a little bit of a tutorial, as this is a tutorial session, on how to use a particular toolbox that we're developing. And spoiler alert, we're hoping you will all adopt. With that, I'm going to turn it over to Herschel, who was really kind of one of the lead people for pulling this whole thing together. Herschel.
All right, so here's the schedule. So I'm just going to talk for 10 minutes and then turn it over to other folks for the rest of the tutorial here. So what I wanted to do is just motivate what led us to pursue this graph-based modeling approach, what it's meant to do. And then I'll talk about the very generic equations we kind of use as the core of this approach. And then next will be Chris, who will give you some more specific examples in different energy domains for how we can use graphs to model real components. So in the title of the tutorial, we talk about multi-domain and multi-timescale energy systems. So what are those and why do they matter? So probably not a secret to most of you that the demand for energy systems to improve in a variety of different figures of merit is really strong, right? And that includes just raw performance, right? The power they can handle, but also the power and energy density, efficiency, sustainability, resilience, and the needs for these figures of merit really drive us towards having greater complexity, connectivity, integration, creates a lot of opportunities for controls that in a lot of ways, if you're familiar with kind of the state of controls and optimization in industry, a lot of the things we can offer at this conference are really under-tapped, I think, compared to what the state of the art in practice is. And so you look at these systems, they tend to involve not just kind of one energy domain, but an interaction of multiple energy domains. So thermodynamics, electrical, mechanical. And as a consequence of that, they tend to involve a range of different timescales. So you think about like very slow thermodynamics, all the way down to sub-millisecond electrical dynamics. Sometimes if you look at the eigenvalues, they can span like 10 orders of magnitude, right? So really a wide range of timescales. And that creates some challenges to design and optimization and even just modeling and simulation. So there's opportunities to leverage tools from our field, but really to do that, we need effective dynamic models, right? I think as control engineers, we all understand the value of having a good model of a system. Those models can come from lots of different places. One would be data-based models, but also physics-based models are really useful. If you're dealing with a system that is inherently energy-based, there are good governing equations that we can use at least as a starting point, like conservation of energy and mass. So we want to leverage those techniques. Just to give two specific examples of places where these techniques work well, you look historically at aircraft, the amount of electrical power on board is increased. This is a logarithmic axis there on the left, so it's an exponential increase in the onboard power. With more power, you also have more heat generation due to inefficiencies. You have to remove that heat, so it creates coupling between electrical and thermal systems. And there's obviously lots of propulsion, mechanical systems in there as well. And then in the last couple of years, probably all seen the explosion in discussion around data centers. Obviously, that requires a lot of power, but again, you also make a lot of heat and have to cool that heat. Cooling often requires water. So there's multiple energy domains, electrical, mechanical, thermal, fluidic domains that all get wrapped up together in these systems. There are a lot of tools out there for modeling these systems. Right. In this presentation, we're really just going to focus on this one approach called graph-based modeling. And we want to be clear, like all these approaches listed and others that aren't listed here can give you a good, accurate model of the system that can be used for simulation and for various levels of controls and optimization. They all have different advantages and disadvantages. Again, we're really just kind of zeroing in on the last one listed there, graph-based models. And so the two things that you're going to see come up over and over again in this tutorial that graphs can do, one is they are graphs. They encode the model in this network structure, and you can use that structure in a variety of ways. And so that toolkit, the techniques you get from graph theory to analyze coupling and decoupling in a system, to combine systems. It all flows very naturally within these graph-based models. And again, as a consequence of using graphs, we can compose graphs, we can decompose graphs. That allows us to build up very complex system from component or subsystem level building blocks. Lets us take a really complex system and break it up into pieces for maybe distributed control. And so we'll show you some of those techniques throughout the tutorial today. All right, so again, I just want to walk through the kind of domain agnostic form of these equations. So we can apply conservation of energy or conservation of mass. I'm going to focus on conservation of energy right now in my nomenclature. There's some seats up here. If anyone is looking for a seat, feel free to come up. So let's say we're applying conservation of energy. As sure you all know, right? A simple expression for that, the rate of energy stored in some control volume is equal to the rate at which energy comes in minus the rate at which energy goes out, right? So we're going to use P here for power. We usually call it power flow. And then if you kind of go one more level into these equations, right? Typically what you see is that the rate of energy storage at a control volume is equal to some capacitance C times a dynamic state, or the derivative of a dynamic state associated with that control volume, right? And then on the right, it's kind of the same. You're going to sum up over all the powers coming in and out of that control volume. And typically these power flows, for us, we're just going to say these are some nonlinear function of no more than two states, as well as potentially a control input. So that is kind of a key assumption we're going to make. But it turns out for lots and lots of different thermal and electrical and mechanical systems that their power flows do just depend on one or two states. And so to make a graph, what you do is everywhere you have one of these control volumes, really anywhere you store energy in a system, you put a circle, and we call that a vertex or a node. Vertex and node mean the same thing to us. And then anywhere you have a power flow between two states, you put an edge, one of these lines, right? And so you form up, this is what we mean by a graph, this network of nodes and edges. And so you can also have boundary conditions to the system, and that could take the shape of exogenous states or exogenous power flows. We typically draw those with dashed lines. So like this dashed circle here would be a state of the system, but not one that we calculate within the model, one that is exogenous to this model. And similarly, we could have dashed power flows, dashed edges as well. Really important thing to point out here, these edges, they have arrows on them, right? That tells us about the orientation of the power flow. It's not an assumed directionality of the power flow, right? So this is our sign convention for what we're calling a positive power flow when we add and subtract them in our state equation. Power absolutely can be flowing in the opposite direction of that arrow. It just would be given a negative sign convention. All right, so if we take all of our kind of node-wise equations, right, we can stack them up in a big matrix equation, and that's all that's happening here. So you take all your individual capacitances of the nodes, you put them in a diagonal, you get a capacitance matrix, you stack your state vector, and then you basically take all the mapping of which edges affect which states, and that mapping is encoded in M, which is the incidence matrix. So this is a matrix of positive ones, negative ones, and zeros, and just tells you which power flows affect which states, right? Which are going in, which are going out. And so here P is just the vector of power flows. And then you can do a similar mapping to any exogenous power flows. So P in here would be any source or sink power flows affecting the system. And D is just, again, a mapping of zeros and ones that tells you which ones affect which states. All right, so you get this nice matrix equation. And in fact, this is a linear function of the power flows. The power flows themselves are often nonlinear. So a couple of observations about this before I hand it off to Chris. So one is we have this diagonal matrix of capacitances. This tells you a lot about the timescales present in the system, right? It's not exactly mapped to that because it also depends on what's happening on the right-hand side here. But generally, you can tell a lot about whether a given state is fast or slow, depending on how big its capacitance is. Incidence matrix M, again, this captures the network structure of the system. So if all you have is M, you can draw out what the graph looks like. And that tells you about really what the structure of energy or mass conservation in the system looks like. So we talked about energy, but I can do the same thing by applying mass conservation. Usually then your states are pressures, and instead of power flows, we have mass flow rates, but everything else kind of holds. And then lastly, as I mentioned earlier, right, our top equation here is all linear, and we kind of push all the nonlinearities into this power flow equation, right? In this case, a vector of nonlinear functions. And doing that is really helpful for analysis. We kind of put all the nonlinearities in this algebraic equation. And we've done things like approximate that with Koopman operators. You can learn these from data if you want. There's all kinds of nice things that you can do when you have your nonlinearities in a structured form. Often what these nonlinearities wind up being for physical systems is they are things like material properties, fluid properties, empirical correlations for heat transfer, right? Things like that that usually are learned empirically anyway. Couple more observations here. So far I've just talked about conservation of energy. That could be conservation of thermal energy, mechanical energy, electrical energy, right? It could be more of those simultaneously. And can't even be applicable to two-phase systems. So when we originally derived this, we focused mostly on single-phase fluid systems. But you can do this for two-phase systems like refrigeration cycles, where you have a refrigerant that is transitioning from a gas to a liquid in two-phase state. There's a little more involved to do that than just these equations here, but there's a straightforward extension that is documented in the tutorial paper we wrote, as well as papers that are cited in that. And then lastly, you don't necessarily have to take your whole system and make one big graph of that whole system all at once. What you can do is define component or subsystem models and then assemble those together. And so you get a really nice modularity of being able to build a library of components that then get assembled. And Chris will show you some of the theory around that, and we'll show you in a toolbox how it actually happens in code. All right, so this is kind of a bullet on each of the presentations we're going to give for the remainder of this talk. So we're going to show you some examples of how to build models in different domains. We're going to show you how this has been used over the last 10 years for control, how it's been used over the last 10 years for design and architecture optimization. Then we're going to show you this new toolbox that's up on GitHub now, where you can start building and analyzing your own graph-based models. Then we'll have some time for future directions and open problems at the end. All right, with that, I will hand things off to Chris. If you want to see the tutorial paper, by the way, there's a QR code for it. So that's on archive. It'll be in the ACC program as well, but you don't want to wait to get access to that. It's on archive too. All right, Chris.
Cool. Thanks, Herschel. Everyone, I hope everyone can hear me okay. My name's Chris Axland. I'm with PC Krause and Associates, and as Herschel said, I'll talk a little bit more about some of these graph-based modeling examples that we've kind of built out over the years. So I'm going to kind of start off repeating a little bit of what Herschel just said. We usually take a component-based modeling approach when we work with these graph-based models. What that means is we build out a library of graph-based models, and then we, using some heuristic knowledge or a schematic like the one I've shown here, we compose those components into a greater, more complex subsystem or system. This is hopefully we can all agree that this is a relatively complex system. It's representative of an aircraft electrical and thermal power system. There's a lot of components in this system. It's kind of small. I'm sure not many of you can read that, but there's kind of this list of components in that system down there at the bottom. And how we approach modeling something that is of this complexity is we'll start to look at what components there are. And we'll build just a model of that component, and we'll figure out, what are some other components of the system. So these are two heat exchangers, a liquid-to-liquid heat exchanger and a cold plate heat exchanger. And we'll build these graph models, and we'll identify where all these things are in the system. We'll look at this schematic, and we'll connect them and build out a really complex looking graph model, right? So this is a graph model of this entire architecture. It has 186 states, 108 inputs. And doing this in this component-based framework is really instrumental. Doing this by hand, writing it equation by equation would probably take a pretty long time. But there's two fundamental pieces to get this far. We need to first build this database, this library of components, and then we need to have an understanding of how we can actually take those components and connect them together. So that's kind of what I'm going to talk about over the course of the next 10 or so slides. I'll preface this with saying, what I'm about to show is not exhaustive. We can't include everything we've done in these graph models in this next 5 to 10 minutes. But hopefully these are some good examples to give you some insights, some taste of what it's like to work with these models. And we'll start where we actually started modeling these systems. We started modeling single-phase thermal and fluid systems as graphs. Specifically, with thermal systems, which obey energy conservation, as Herschel had mentioned earlier. The key thing to building a graph model is understanding two things. How is energy stored and how is energy transferred? That gives us insights into how we model and represent our vertices for storage and how we represent our edges as energy transfer. For thermal systems, if we want to think about how energy is stored, thermal energy is stored, it's done in thermal masses. We associate with those thermal masses a temperature state. If we think about how energy is transferred, how thermal energy specifically is transferred, we can think back to our undergrad days of heat transfer textbooks, and you'll see these four things listed: convection, advection, conduction, and radiation. Those are our four primary modes of heat transfer. In using these kind of fundamental building blocks, we can build a wide variety of thermal system models. Over here on the right side of the slide, I've put together this example of a cold plate heat exchanger. If we want to build a model of this cold plate heat exchanger, we ask ourselves these two questions: how is energy stored? How is it transferred? This is a cold plate heat exchanger you might find on a CPU on a personal computer. Energy is stored kind of a couple ways here. One, it's got this block of metal there on top. That's what interfaces with your CPU. It's a thermal mass that'll store some thermal energy. So we associate with that a vertex in our graph model. Also within that cold plate, we have some fluid, right? That fluid itself stores some thermal energy. And so we can associate with that fluid volume, we can associate a temperature state as well. So that's how energy is stored. Next question is, how is energy transferred, right? We're forcing fluid through this cold plate, so there's some convection happening in that system. You can see there's some convection happening between this wall and this fluid. But you also have fluid moving in and out of this cold plate as well. And so that's advective heat transfer. And you can kind of see where these terms show up here. Again, I'm not going to go into too many specifics on how we arrived exactly at that, but hopefully you can see where some of these pieces start to come together. Again, it's all about understanding how is energy stored, how is energy transferred. But it's not just energy systems. We also talk about fluid systems, which as Herschel mentioned. We can model using mass conservation in these cases. In these situations, we can model storage as pressure states, whether you're storing mass in pipes, tubes, tanks, etc. And you measure the edges are then representative of mass transfer. So things mass, again, are like tubes, pumps, valves, etc. And I'll show over here on the right, example of a pretty simple thermal cooling loop, a pumped system. More recently, we've looked at these two-phase thermal and fluid systems. These are a little bit more involved to model. The reason is that their energy and their mass conservation behavior are tightly coupled. And so we have to make an adaptation to our modeling framework to adapt for that. And what you end up seeing is that we actually will represent the vertices with two states. And this is kind of the inception of what we'll call the multi-state vertex representation. In here, we model both the enthalpy dynamics as well as the pressure dynamics all within one node on the graph. We've also done a healthy amount of work on electrical and mechanical systems. These are modeled in fundamentally the same exact way. I hope a lot of us are familiar with this electrical and mechanical analogy, right? Springs are a lot like capacitors, masses are a lot like inductors, so on and so forth. And we really exploit that analogy when we model these two types of systems. I like electrical systems, so I'll show my examples for the electrical, and I'll leave it to you to think about more critically about the mechanical, whether it's rotational, translational. But electrical systems, like before, these are following energy conservation. How is energy conserved, or how is energy stored in an electrical system? There's two primary mechanisms. We got capacitors, we got inductors. How is energy transferred? Well, you can have just classic power transmission, which is voltage times current. You can have power transfer due to loss, things like resistors, in the electrical domain, dampers, and mechanical, or you can have some level of power conversion. This is like electrical transformers. If you're mechanically minded, maybe you like levers and gears. But these are, this is the general approach we take to modeling these type systems. These are the things we're thinking about. Over here on the right, I show a simple example of an electrical power converter, something that will buck a high voltage input to a lower voltage input on the output side. We've built a ton of components over the course of the past decade. These are all in this graph modeling toolbox that you'll hear about in just a few presentations. But really the core thing that if you're going to take anything away from this is really just understand how is energy stored, how is energy transferred. That's kind of the big thing when it comes to building single component models. The second thing I wanted to talk about was how do we actually then take these models and compose them into something greater? There's two ways. There's two types of connections. We have vertex connections and edge connections. Vertex connections are used when two components share the same state. Edge connections are used in situations where you connect two components where the power out of one is just the power into the other. It's kind of a little vague with this example, so I'm going to kind of move on to hopefully something a little bit more interesting. We're going to build a model of a liquid-cooled motor, and we're going to throw a controller on this motor so we can adjust its speed. As you push power through that motor, we want to keep it cool, so that's why we're going to equip it with a cold plate heat exchanger. So building this larger system that we have in mind, how are we going to do that? Well, if you wanted to build this in reality, what would you do? Well, you'd probably start by connecting the motor to its motor controller. And what are you going to do? You're just going to solder the leads of the one to the leads of the other. And that is effectively in this framework an edge connection. Like I showed over here on the right. The power that will leave that power converter is identical to the amount of power that's going to enter that electrical motor. That's an edge connection. Power into one is power out of the other. That motor will generate heat, and it will impart that heat on the casing of that motor. The motor will start to physically get hot. That's the temperature state of the motor. But also, if you go over here and look at the cold plate, that cold plate, remember, it's got this brick of metal, right? So you can make this analogy that says that this cold plate wall, this chunk of metal, we can say is the same thing as just the motor wall. And we can call that a vertex connection. So we go and compose these systems. I'll show an animation here. We're going to take this electric motor and we're going to take those edges. We're going to look at that input edge to the electric motor. And we're going to take that power converter and we're going to overlap those two edges. That's our edge connection. We want to now attach a cooler to the electric motor. We're going to look at that temperature state there. And we're going to take this cold plate heat exchanger. We're going to overlap that wall of the heat exchanger, put it on that motor wall. And what you end up with is, this more complex, this larger system or subsystem model of this liquid-cooled motor. And it's very easily identifiable, what states your power converter states, which states your electric motor states, and where your cold plate states come from. So hopefully this gives you kind of a taste of some of the models that we've built, and what we've been able to work with over the past years. I think at this point, I'm going to hand it off to Justin to show you some of the control work that we've done in this area.
Thanks, Chris. So as you mentioned, I'll be talking about how we've used the structure of graph-based models and exploited that structure to develop various different types of controllers. And so this is the first of two talks related to the applications of graph-based modeling. I'll focus on control design, and then our next talk will be on control co-design. And so first off, I just wanted to motivate what are the control objectives and challenges associated with modeling and controlling modern energy systems. So that way we can talk about the value of graph-based modeling in context. And then we'll go through various examples where I think are just really hallmark examples of how the specific structure of these graph-based models enabled some type of analysis or control design that would have been challenging otherwise. And so that includes passivity-based decentralized control, hierarchical architecture design, so not just the controllers within the architecture, but the actual structure of that architecture, how we can improve the linearization of these models by looking at the specific structure of those power flows along the edges, and then just to demonstrate how we've develop models and control both in simulation as well as experimental validation. And so I'll show a few of those things. So just, with a lot of systems, the objectives for control for that system really can be broken into three categories of performance, efficiency, and safety, right? Performance is really what you think about. What was the system intended to do? But of course, we want to achieve that functionality with it while consuming as little resources as possible. So that efficiency metric is always in there. And then for these, energy systems, there's always a safety concern. There are critical constraints on both your actuators as well as your states of the system that need to be satisfied in order to guarantee safe operation. And the really interesting thing about this is that the first two objectives of performance and efficiency almost always push the ideal operation of your system up against some of these constraints. And so for control design, you're always trying to balance pushing your system to the limit, but guaranteeing that you won't go over that limit. And so that's where having really accurate models is so important. I know in the age of data-driven modeling and things like that, there are some new techniques that might be able to handle this, but this is where having a really accurate model, at least in our experience, has been useful for things like model predictive control design, where you can actually establish some theoretical guarantees and ensure robustness to various types of disturbances and model error. So those are the objectives, but for these energy systems, there's a number of challenges. The main ones are that, as Chris and Herschel mentioned, that we have lots of different energy domains interacting with each other. And those interactions are highly dynamic and highly complex and evolve over a wide range of timescales. Just to give you a sense of this, we like doing a lot of aircraft examples. So here's a schematic of, let's see, 6 different subsystems within an aircraft, including the engine, the fuel system, the thermal management system, avionics, hydraulics, and electrical. And every one of these arrows is the transfer of energy from one system to another, where red denotes heat transfer, green denotes electrical energy transfer, and there's a few black edges denoting mechanical energy transfer. What's not shown on this, the idea of this is just to show that this is a kind of a scary problem with lots of interactions that need to be accounted for. But what's not shown is that all of these interactions occur over different timescales and are highly nonlinear. And so we need control strategies that can scale up to these type of complex systems while actually optimizing with respect to these nonlinearities instead of just trying to be robust to them, because we're really trying to maximize that performance and efficiency. And then, of course, we know things like the temperatures of batteries need to satisfy hard upper bounds on their temperature to prevent things like thermal runaway. And as I mentioned before, if we want to maximize the efficiency of the system, we might want to try to minimize the cooling going to that battery pack. And so in some cases, the ideal operation would be to get as close to that upper limit as possible while guaranteeing that you won't exceed that limit. And then finally, as Chris mentioned, some of our examples, these systems are quite large. And so we want modeling and control techniques that can scale to complex systems and can be compositional in nature so that we can develop models and controllers for systems with hundreds of states and inputs. So in this context now, we see that there's value in graph-based modeling, both from the modeling side of things as well as the control side. Now, I'll hopefully demonstrate some of that through this talk. From the modeling side, this first bullet seems obvious. We wanted a modeling strategy where conserved quantities that physics tells us should be conserved, we want that to be conserved in our models. And while that seems obvious, in our experience, when we start working with complex models that aren't graph-based, it's very easy to overlook certain power flows. You can have inefficiencies in your system that are creating significant amount of heat that are very easy to overlook if you don't have a structured modeling approach that requires you to balance everything. And so we were dealing with complex Simulink models that, when you start looking into it, you see tons of power that just are going off into the abyss that weren't being accounted for. And that was one of the motivations for this graph-based modeling approach. We also want to make sure, as Chris mentioned, that when we model all these different components, that we're making sure from the very beginning that these models can be composed in a meaningful way to create more complex systems. So we can call that maybe compositional consistency. And this imposed structure helps guarantee that. And then finally, from the modeling point of view, it's just really enabling to be able to break up the modeling into 2 distinct steps, as Chris mentioned. Figuring out the structure of your model in terms of how many vertices should there be, and then what should the edges be between these vertices, and then focusing on all the nonlinearities. And that's because all the nonlinearities are just embedded within those power flow equations for each. And as you start to model more and more complex systems, that's where this modularity comes in. You can focus on modeling one edge at a time. And that is what we see as one of our main enablers for scaling. And then when you go to control design, as we'll see through a few examples here, there's lots of different ways of modeling the systems, but this is one of those modeling approaches that has a structure that can be exploited directly for control design. We can also use these structures for systematic hierarchical decomposition, so figuring out how to take a large system and break it up into smaller pieces that have minimal amounts of interactions so that you can achieve decentralized, distributed, or hierarchical control with less conservatism. That structured nonlinearity allows us to use new linearization techniques that go beyond standard Taylor series linearization, as well as we can explore architecture design using these graph structures directly, and that'll be the focus of the next talk. So just to give you an example of how this graph-based model can be exploited for analyzing the behavior of dynamic systems as well as for control design, let's just consider a simple subsystem within a larger system. This subsystem will have NV vertices. In this case, there are 5 vertices denoted with the circles with the solid black borders. We'll also have NE edges. In this case, there are 6 edges, and these are the solid black arrows. And then we'll have our subsystem interacting with its environment or neighboring subsystems. And so we'll have power flow going in. In this case, we have 2 power flows going in, and those power flows directly affect some subset of the states within that subsystem. And so we'll label those as X superscript N. Then we'll also have power going out of the subsystem. In this case, we only have 1 power flow going out, and that could be affecting some neighboring downstream system or just power flow going out into your ambient environment. But we generally assume that that downstream system or environment will have some sink state X superscript T. We also assumed that these power flows are nonlinear with respect to the head and tail vertex states, but would be affine in control with some control input associated with that edge. And under this framework, which is, I think, still fairly general, we were able to show that these subsystems are passive with respect to a certain choice of inputs and outputs. And that's what this structure allowed. We were able to identify what those outputs should be for systems that otherwise it would have been hard to identify what a passive combination of inputs and outputs would be. So in this case, if we consider the inputs to be the power flow coming in, the controllable inputs, U, and then the inputs associated with these sink states, and if we map that then to a set of corresponding outputs, basically these inlet states, some nonlinear expression of our outputs, which is a function of our states and our sink states, and then the power flows going out, well, it turns out from this input vector to this output vector, we have a passive relationship for a general class of systems modeled with this graph and this nonlinear power flow expression. So what does that do? Passivity is a nice way of looking at the stability of your system, and it has this nice compositional property where if you have 2 passive subsystems in negative feedback with each other, passivity is preserved. So using that, if we can demonstrate that each subsystem within our system is passive, and then show that all connections between subsystems or systems are through a negative feedback connection, then we can then guarantee that our overall system is also passive. So that would be in an open loop sense, just to prove something about the open loop properties of a complex system. But then in closed loop, if we start designing controllers in negative feedback with each subsystem, where we can control the inputs to each subsystem based off of some measured outputs, and we have to choose that output vector carefully, but that's where the structure of these models comes in, and it tells you what that output structure should be. Then as long as our controller design ensures passivity between the inputs of that controller and the outputs, then once again, we have 2 subsystems in negative feedback with each other that are both passive. And now you have a passive closed loop system, which you can use to guarantee closed loop stability for complex nonlinear systems. And so this can be for centralized control design, decentralized, distributed, or hierarchical, as long as those low-level controllers are guaranteed to be passive. From the context of MPC, ensuring passivity for MPC doesn't come for free. But if you add some type of passivity preserving constraints, then you can just build that into the series of constraints within your controller to make sure that your controller is either always passive or passive on average. And that's what this kind of type of equations would ensure, that you could behave in a non-passive way temporarily if that helps you achieve higher performance. But as long as you preserve passivity overall, then you would guarantee closed loop stability. So then when we started looking at scaling this up to more and more complex systems and wanting to develop control strategies that can handle that complexity, we were realizing that the way that we think about complex systems is naturally through a hierarchy. We have the entire system. In this case, we were thinking about aircraft, so we were talking about like a vehicle level, and then that vehicle is comprised of multiple systems, and then each system is comprised of subsystems and so forth. And we go down to component and individual physical signals. Well, why not have a control strategy that just exactly mirrors that dynamic or the structure of those dynamics. So that was our intent, is to go and design hierarchical control strategies where these upper level controllers are thinking about just the slowest timescales of your system. They update at relatively slow rates, but they're looking far into the future to kind of plan out what the system should be doing over, let's say, several hours. And then as you work your way down your hierarchy, each controller is responsible for a smaller and smaller portion of the system, is making decisions more quickly, and is looking over a shorter prediction horizon. So this could be, every circle of these could be MPC controllers, in which case the challenge is how do you achieve coordination between those controllers, and how do you guarantee things like closed loop stability and constraint satisfaction and things like that. But some of these lower level controllers could just be static feedback control or PI or something like that. So then how do you figure out what that structure should be? How many controllers should you have at each level? How many levels should you have? Well, that choice should be dictated by the dynamics of your system. And so that's what this graph-based modeling allows you to do. Here, Donald, in his work, looked at modeling a electric vehicle energy system as a graph. In this case, this graph has around 50 states. You can kind of see the structure of that here. And then all 50 of those states are shown as this on the horizontal axis of this dendrogram. And he developed a an energy-based distance metric to figure out how tightly coupled neighboring vertices are. And two tightly coupled neighboring vertices will show up as a connection that's low down on this dendrogram. And that basically tells you that if you're designing subsystems, you really should have those two subsystems or two vertices within the same subsystem. And then some of the connections that occur up here means that those parts of the system are more decoupled, and it's better to divide the system along those lines. And so this is a nice way to design the architecture of your controller directly from the structure and the dynamics of your system, which once again is exploiting this graph-based structure. Then we've also seen that the graph-based structure, the fact that all the nonlinearity lives along the edge allows you to do some nice things beyond just linearizing a general nonlinear state-space model using Taylor series approximations. So in this case, Herschel and his student at Penn State looked at, the nonlinearities are stored on these power flow edges. Well, you can actually create a lifted graph where you introduce auxiliary, basically fictitious vertices that are associated with these different power flows. This augmented graph still makes sure that conserved quantities remain conserved. So that property of this graph is maintained. But now you can go and simulate the nonlinear system to estimate the dynamics of these new auxiliary states. And these will be linear. So this lifted system is linear, but it's designed to closely approximate the nonlinear system. And so it turns out that they've shown that this linearization approach, which is kind of similar to a Koopman type lifting approach, it achieves better results, more accurate models compared to the Taylor series approaches. And then when you go and use that for MPC, that means you can get higher performance controllers with less conservatism. And then as Chris mentioned, he actually showed basically the same exact figure. We have scaled this up. To my knowledge, this is one of the most complex systems that we've applied graph-based modeling to, with just under 200 vertices and over 200 edges, and a little over 200 controllable inputs, both continuous inputs and on-off valves and various types of binary inputs. And so in Matt Williams' thesis, we developed models of these systems, both the thermal and the electrical side of these systems, and a hierarchical model-based controller based on those models. So the idea here is that we have scaled this up. We believe that could scale further, and it's all just based off of this modular modeling. And then finally, one of the main takeaways I hope you come away with was one of the things that we learned and we were kind of surprised by when we first started this. We kind of fully expected that to be able to capture the complex dynamics of a true physical system, we would need a lot of these vertices because things like temperature are spatially distributed. Here we're showing a thermal image of a cold plate, and you can see the temperature variation across that cold plate. But it turns out that we can develop a very accurate dynamic model with just two states. And that's what Chris mentioned. One state corresponding to the temperature of the fluid inside the cold plate, and one state corresponding to the metal of the cold plate. And these are averages because everything is distributed and throughout the physical part of this component. But that's one of the enabling things here, is that if you just want a control-oriented model, you can get away with far fewer states than you might expect. And so we developed these models for fairly complex fluid thermal systems. We've then extended it to hybrid electric UAV powertrains, as well as hardware in the loop systems where we have a combination of hardware and simulated systems, and the controllers all running in real time, all based off of these graph-based models. So hopefully that gets you a sense of how these models have some structure and how that structure can be used from a modeling standpoint, but also from a control design standpoint. And then I'll turn it over to Donald to talk about how we can use this for control co-design. Thanks.
All right, so on the second half of our applications, we're going to talk about control co-design and dynamic optimization. So just for some motivation, which I think a lot of you guys are familiar with at this point, we have our next generation energy systems they have escalating requirements, right? Power for AI is especially one that's being focused on a lot right now. That means we need better plant designs for these systems. It applies to electric vehicles, say we're trying to do battery sizing. It applies to our grid architecture. How many inverters do we need? Where are we placing them? Do we need stationary energy storage? And then it also applies to what a lot of the microgrids are powering right now, which is our data centers and the thermal management systems are associated with them. And of course, these physical designs, the optimal version of them is going to be associated with their transient behavior and how we control them, right? So what we need at the end of the day is model-based design tools that support control co-design, doing both of these things at the same time, optimizing our controller, optimizing our plant, and trying to get the best thing out of that, right? Graph-based models that have an underlying connection to our energy dynamics are very valuable for approaching these types of problems and setting them up. So on one half, if you're going to do let's say component sizing, you're trying to select where you should place your components or how many that you need, you can associate these with features of a graph, right? If you're trying to size a component, that's related to your vertex sizes or your capacitances. It's related to your edge thickness, if you want to say, right? And then if you're trying to decide if you need a component or not, you can say take out those edges as well. So these design options can be correlated directly to what our graphs have. And then if you go to a step beyond just talking about edge removal, you can look into architecture design exploration and trying to say sort of along the lines of what Chris was talking about earlier. And we can combine these different component graphs up into a larger system and looking at all the different options that are feasible for that type of thing. So what I'm going to do is I'm going to focus on the first half of this, which is more on the sizing of our components and maybe a little bit of topology optimization here. And then Nir is going to dig deeper into the architecture design exploration. So control co-design, the way I look at it is it's broken down into basically 4 steps at the end of the day. You have some design variables or decision variables, your plant design variables, I'll call them theta. Your controller design variables, I'll call those phi. You're trying to select those, right? The big takeaway I want you to take from this slide is that you want to map your plant design variables to the model that you're trying to represent. And that's what these graphs can do pretty easily. So if we have our component model that's produced by the toolbox, right? We get the systematic equations that are coming out of that. We can augment those equations by adding in this psi C and this psi matrix to scale our capacitances, to scale our vertices, right? And to scale our edges or even remove or add or remove them, right? So we end up just augmenting a couple new vertices or matrices to just scale our components in these systems. How you can use this, right? I'm a battery person at the end of the day. Let's say you have a battery that's represented by an equivalent circuit model. Of course, there's a lot of different representations. We have a graph-based model, but now I know a battery cell isn't going to be enough to power my electric vehicle. So how do I scale up to consider a bunch of cells that are going to be in series and parallel? You could connect each separate cells model separately, or you could use some predefined relationships that are easily pulled from the conservation of energy to scale up this graph-based model in terms of its vertices, right? Most of your capacitances are going to scale up proportionally with your number of cells in series and parallel. And then in terms of your edges, the stuff that's in green here, most of those will also scale up in terms of the number of cells that you add in series or parallel, but there's a few relationships where you'll have the inverse of that. The big takeaway here is that you can take your conservation of energy relationships and map them to changes in the graph-based model very quickly.
right? Of course, if you're doing optimization, you should have some sort of objective function. We have traditional objective functions that have been explored in, great detail, state tracking, input cost, size, and things along those lines. But the graph-based models also leverage a few things that are useful if you're really focused on energy. So I like to look at power tracking problems because that can help coordinate your subsystems by making sure, if this guy is producing a certain amount of power, that the other system is expecting that same amount of power, right? You can also look at your energy stored, and that comes directly from the underlying relationships of these graph-based models, and calculate out total energy in the system or for specific vertices or components, right? After you have that, of course, you need your different constraints. There are state dynamic constraints that comes directly from these models. The one I want to point out here is the control law. This can tie in nicely to what Justin was talking about earlier, right? We have so many tools that are available for these graph-based models in terms of developing our control laws and MPC. You can fit that in here. You can also fit in PID-based control. You can fit in even model-free based control if that's something you want to approach here. And then you mash all these things together, you get your control co-design problem built around this. One last advantage that these graph-based models have when formulating your control co-design problem is just like I said, like where Chris was talking about how you can combine these things together, you can also take your graph-based models apart. So there has been some work, I think this was Kayla's work, where she looked at your control co-design problem, decomposed it into a bunch of smaller subproblems, making it a little bit more efficient to solve, right? Or even more so, being able to explore a greater design space. I'm going to talk about a couple examples, just kind of high level here. We've talked about aircraft thermal management and aircraft design or aircraft control in the last few slides. I'm a person that likes to keep my feet on the ground, so I'm going to talk about ground-based electric vehicles. So if you want to optimize for an electric vehicle, its powertrain and its thermal management system, big design variables that you're looking at, your battery pack size, your motor sizes, how many motors you should have, whether you should use air or liquid cooling. You can generate a graph-based model for something like this. If you want to do control co-design, you can, or you could just define your input profiles a priori and just kind of make it more about plant-based design. And if you have different metrics, you want to minimize your maximum temperature of your inverters, let's say, you want to make sure your vehicle goes from 0 to 60 in a certain amount of time, these things are easily implementable. So I'm not going to go through the math on this. I'm just going to kind of show a visual representation of what some of the prior work has done for these things. And, I could show radar plots, but instead I'll just show you the graph and what it looked like before. Then we apply a genetic algorithm. We use some smoothing to remove our discrete options and turn them, or rather transform them into more continuous ones. And so if you have an initial battery pack power or battery pack for your powertrain, maybe that thing is a little bit too large. And so your optimization problem would say to size your vertices down for this system, right? To highlight the major changes from before to after here, it's kind of in the highlighted blue. The big changes are that battery pack shrunk. We do want a second motor in this case, but it's used just minimally. So we don't need a large motor. We don't want to add in too much extra weight. And our power electronics, our inverters, our converters, all the power is being put through those things. So we probably want to dedicate liquid cooling for those components in specific in order to make sure that they don't heat up and have higher failure rates in the future. For our second example here, again, I like to keep my feet on the ground, and let's go with the hot topic of microgrid and data center control co-design. What if you want to design your data centers to be a little bit more environmentally friendly, right? So let's say you're just trying to size your battery pack on the microgrid side for now. You have a model-free perturb and observe based controller where you're trying to choose the duty cycle step. The main thing here is what are our objectives that we're focusing on? Well, we can look at the emissions that we get from manufacturing. We can look at the waste heat that's generated from operation, right? And we can look at e-waste, or essentially degradation of our components, because we don't want to replace those too quickly, right? I'm not going to go through the graph-based model on this part here, but that's how we actually built this control co-design problem. And I'm not going to cover everything that's highlighted here. I want your attention on the blue part. The y-axis is our manufacturing objective. The x-axis is our operations objective, or waste heat. And if you're building a renewable based microgrid to power a data center and its thermal management system, you shouldn't worry about waste heat for the most part, because the damages that that'll do to the environment are completely dwarfed by whatever manufacturing resources you're required to build your battery pack and the system in the first place. Now, that's not going to be true for everything. This is kind of like it would slide depending on how much you're using gas turbines and things like that to generate your power. But that's something that we were able to look in and discover by setting up our graph-based or our control co-design problems through these graph-based methods. So that wraps up my part. I'm going to hand it over to Neera so she can get into the details on architecture design exploration.
Thanks, Donald. All right, so as Donald said, I'm going to talk a little bit about how we can also use graphs to explore different architectures, and specifically I'll focus on thermal systems because that's what we're talking about, but these ideas could also be broadened obviously to other types of systems. And this idea of exploring different architectures is not new for thermal systems. It's typically done, but largely at steady state. So certainly there are many different companies that build different types of thermodynamic systems or thermal management systems, but they're going to use steady state models and look at their operation, usually around prescribed design points, for example, to assess performance. But for all the reasons that we've cited already in this presentation, there's a growing interest in the dynamic performance of these systems. And to build on what Donald was talking about with controlled co-design, the whole motivation there is saying that those design decisions impact the transient performance of the overall system, and we want to think about that in tandem with control. And so similarly, if we're going to explore different potential arrangements of components, hence an architecture, to accomplish different types of thermal performance objectives, it makes sense that we would want to be able to actually evaluate the dynamic performance of all of those different architectures. So to do that, we're certainly going to want or need transient models of all of them, but that's a lot to do to derive all those different system models. And so what we want to do again here is exploit the modularity of graph-based models of individual components to actually sort of auto-generate, if you will, system level graphs of those different prescribed architectures. And as soon as we do that, again, we have now the ability to quickly evaluate and assess the performance of all of them. Now, there are some challenges that come with doing this connection. Chris talked a little bit earlier and showed visually how we connect edges and components. And when all of the components that you are connecting are represented by dynamic graph models, that's a little bit easier. But one of the things that we often find, and for those of you who might be familiar with modeling thermodynamic systems, is that there are components we model algebraically as well. And so we often end up with these differential algebraic systems. And so in that case, it doesn't quite work as seamlessly to just connect all those ODEs. And so something that we've done is shown how you could build a single unified system graph with a state vector that contains both the dynamic states that come from those graph-based models, as well as sort of the component ports, which we're going to represent with these, let's call them pseudo-states or algebraically, and I'll talk more about that briefly. So we're going to do this by building a system graph that merges the connectivity information and those component models. So we can define this vector X that has our dynamic states as we normally do and augment it with these system states. And so these system states represent fluid states at the component interfaces. They are algebraic, so there's no ODE associated with those. And then, of course, we have our dynamic states that represent all those different states that were talked about earlier, depending on, again, what type of energy system you're modeling. This is an example on the right of what this could look like, where you might have two heat exchangers where all of these solid nodes represent dynamics vertices, and these ones in dashed outlines represent boundary conditions. And then the ones with double lines are really algebraic in nature. Okay. So each of our dynamic component graphs can be represented in this way. This looks a little bit different than what Herschel talked about earlier. This S dynamic represents a case where we're accommodating multi-state vertices as well. And then each of the algebraic relationships that are contributed by any algebraic components that you want to include in that system graph, we can represent with a residual constraint f of x. So fundamentally what we're doing is saying, let's go ahead and build this DAE system where we can evolve and simulate those dynamic equations subject to the constraints imposed by those algebraic relationships. And so as an example, so we'll define this f of x, where f dynamic is really just 0, but this f algebraic, let's use this example here, represents what those equality constraints should be that need to hold at all time. So for example, this node 1 is a boundary condition, and so its state, if you will, should just be equal to what that boundary condition value is. If we're just passing along that value from this node to node 2, x2 should be equal to x1. And then the relationship between x2 and x3 in this case is just the algebraic relationship that we're using to describe the pump. Okay. So there are many DAE solvers that we can structure our equations in such a way that it can solve that and distinguish between these equality constraints representing the algebraic components and the dynamic equations. And so ultimately what we do is formulate this residual vector that's driven to 0, or essentially the DAE solver is going to find the combination of states and that satisfy both algebraic states and dynamic states that satisfy this relationship and derive this residual vector to 0. Okay, so that's a way that we've used to sort of, again, auto-generate, if you will, or connect all of these different components to build these system graphs. Once you have that, you now have the ability to, like I said, explore many different architectures. There are many algorithms already out there for enumerating all sorts of different architectures, given some prescribed number of components subject to whatever feasibility constraints you might impose. So let's suppose that you've already enumerated all of those architectures that you're interested in. You can then go ahead and actually build all of those system graphs. And then at that point, you can think about actually optimizing all of them, maybe with respect to different cost functions, really utilize them in any way that you'd like. Some work that we did was to consider an air cycle machine. So going back to those craft examples, this is a single phase thermodynamic example. This is a standard 4-component air cycle machine architecture. But what we did was say, well, what if we had multiple turbines, multiple compressors, heat exchangers, rammer flow paths? How might we connect these in different ways? What are all those possible combinations of 4, 5, 6, and 7 component architectures? And what is the right cost function to use to actually optimize the performance? And we also, again, very specifically here, have these dynamic models and want to understand the behavior of them subject to dynamic boundary conditions. And these particular ones really correspond to sort of an ascent, some high frequency altitude changes in flight, and then maybe a landing condition. Okay. So what we did was auto-generate all of those graph-based models using those components that we talked about, and then optimize them using Casati. And this is, again, I'm giving a very brief snapshot of the results. So if you're interested, I would point you to this article, and it's also cited in the tutorial paper. And here, this was sort of a control co-design problem to the extent that we were optimizing system parameters, and in this case, an open loop control sequence for the bleed air mass flow rate. And the kinds of things that this enabled were essentially a push button approach to optimizing all of these architectures and exploring them. And because of that, we could also just redo that whole process with subject to a different optimization or objective function. So this figure here is showing a histogram of about those 100 and almost 70 architectures. In this case, we optimize them with respect to total entropy generation. So we were looking at second law, thermodynamic efficiency metrics, but also assessing how they performed across sort of baseline metrics like bleed air mass flow rate. And the kinds of things we found is that there was a 25% difference among all of these architectures, which is pretty substantial. So that tells us there are some architectures that are much better performing than others. But among the very top ones, with respect to the cost functions of interest, only a 1% difference. And so what that helps you to then start to do is analyze. This is an example of what the top 3, and I won't go into the detail of the differences here. You can see we have a 5-component architecture and then 2 7-component architectures. But we also, because these were optimized dynamically, can actually look at what that dynamic performance was and understand, well, what's leading to those differences? If there's only a 1% difference in our cost function, maybe there's other behaviors dynamically and how these systems are behaving that are actually interesting for us to understand. So I'm going to stop it there and then hand it off to the next speaker to talk more about, I think, the toolbox. So, there you go.
All right, so I'm Joe Pisani. I'm a first-year PhD student at Penn State, advised by Dr. Pangborn, and I'm going to be talking about our open source graph-based modeling toolbox, referred to as GMT. So a little bit on the motivation for the toolbox. At this point, we've kind of talked about all the benefits of using graph-based modeling for energy system applications, which led us to think, how can we bring this to the community by having a framework in the form of a toolbox? There has been some prior toolboxes developed, but they were in a closed source code base. So with this version, we want to make it open source for collaboration, which led us to the last part, is seeing this toolbox as a platform for continuing research. So the goal here was to build a new open source MATLAB toolbox to apply the lessons learned over the past 10 years or so. The vision for the toolbox is here, starts with plant modeling, moving to control synthesis, followed by plant and control optimization. So a little bit on the structure of the toolbox. We're using object-oriented programming, and this allows us to have a modular graph class structure. So component models and system models have the same structure. We can use the same methods to operate on that data. And with that, we're going to have a component library. There is a component library in the toolbox that has commonly used thermal and electrical system component models. And lastly, there's some built-in automation for those tasks that are commonly used. You can think about the graph toolbox as being broken into a structure and metadata. The structure is kind of the mathematical description. It tells us how the edges and vertices are connected through an edge matrix. And it tells us the mathematical description for the power flow of the edges and the mathematical description of the capacitance and the state derivatives. On the other hand, there's metadata. We want to parameterize our models. So we can use scalars or lookup functions to do that, as well as defining the inputs of our model and ports, how they can be connected together. Some system requirements for the toolbox: you'll need MATLAB, symbolic state toolbox, Simulink with Stateflow, and we verified this on Mac OS and Windows. Here's our GitHub page QR code. The first thing I want to talk about with the toolbox is component modeling. We have a library right now with single-phase thermal, as well as some electrical and mechanical. Right now, this is under active development. We expect to be adding more component models over time. The first example I want to go over is a fluid tank model. It's single input, single output advection, and storing heat in the fluid of the tank. And to create this model, or create an instance of this model in the workspace, we have a class GMT_tank, which is our generalized structure for a tank model. Every component model, the first input argument is going to be description of this instance. In this case, we're going to be calling this one main tank, which is a string data type. We're going to be assigning it a workspace variable name, also main tank. It's best practice to name them the same for traceability. When you do that, you'll have an object in the workspace, MATLAB workspace, with a lot of data associated with that object. So now that we have our object in the workspace, we can interact with this object. There's several ways to interact. We can generate reports on that data to understand how to connect the model together, understand what the initial conditions are, as well as plotting that graph model, adding initial conditions, building simulation files. So in this example, we're going to be just plotting the graph structure in MATLAB. So we have our main tank object in the workspace, and we're going to be calling the GMT plot graph method on this object. And when you do that, you get a figure in MATLAB. And in this figure, the graph on the right is the energy system graph, and there's a graph on the left. In this toolbox, we're modeling the tank mass state as a separate disconnected graph. There are some report functions in the toolbox. This is another way to interact with the data. We can generate some tables related to the edge and vertex information if we're first working with a model and want to understand a little bit more, understanding what the initial conditions are, inputs, parameters, etc. And to do that, we're going to be using the same syntax. We're going to be calling our object, followed by the method. All the reports are abbreviated GMT_report. In this case, the graph report is graph_graph. When we do that, we get a table in the workspace of the data of this model in more of a human readable form. We're going to be zooming in on the vertex information here. So this tells us a description of all the vertices in this model. We have the units associated with each of those vertices, as well as the power flow equations. And the same is for the edges as well. Next is adding initial conditions. So initial conditions can be added to models, but we have to understand what are the initial conditions that need to be assigned. There's a report for that. In this case, it's report initcon. And this will tell us that we have two dynamic states for our main tank, temperature and mass, corresponding to X1, X2. Right now, the variables are unassigned, and the state variable units are Kelvin and kilogram. So it's two ways to add initial conditions to our model. The first is when we instantiated our model. In the first example, we can add an optional input argument followed by a row vector of those initial conditions. And the thing to note here is all the initial conditions need to be assigned for our model. The other option is we can add initial conditions to our object that is already in the workspace by operating on that object using the GMT_nitcon method followed by the same row vector. The key thing here is we also need to reassign the workspace variable name again so we can update the metadata of that object in the workspace. Next, I want to be going over a simple connection of our fluid tank model, main tank, with a split junction model. We're going to be connecting the fluid tank advection outlet to the split junction advection inlet. And then we'll have our simple system model here. And what that looks like in code is you have an array of primary objects, an array of secondary objects. The key thing to note, they're different because all the equations are inherited from the primary object. So the order does matter here. In this case, we're connecting two edges. So the edge equation is going to be inherited from the main tank object. Next thing we have here is a port array. This tells us what port of that model that we're connecting together. And the last line there is a syntax for generating a system model. We have to call the GMT_graph, which is the superclass for all graph models, followed by the combine method, giving a description and passing it the two arrays. One thing, there's another report to understand what the ports are, so you understand what you're actually connecting together in the models. So we can see here in our connection report, port 2 corresponds to the advection outlet. It's an edge connection corresponding to element 2, where the tank split is advection inlet. It's also an edge connection corresponding to element 1, meaning edge 1. Then we can plot this graph. So this is the system graph of this model. On the right, this is the energy system graph, and this is our tank mass state graph. Now that we have our system model, we can get the nonlinear dynamic equations for this model. This is the same process for component models. This example here is just a system model, and it's just a property of your object. So here it's system, and then there's a subproperty expression, and in the orange box there you have the nonlinear dynamic equations. You can also generate a linearized state space model from that object by calling the GMT_control model. There's three variables that are returned. They're symbolic equations corresponding to your A matrix, B vector, and an affine Z term. Some more complex examples that we've used with this toolbox is creating a PTMS model, which includes multiple tank models, split junctions, heat exchanger, and a turbine model. And we've generated with this toolbox specifically, a complex PTMS graph to use for optimization, simulation, and control. The last thing I want to talk about is simulating models. There's two ways to do that. The first is through the command line, and the second is through Simulink. Through the command line, there's another method, build simulation. This will build simulation files for MATLAB, and there's only one input argument, which is the save file path. You do need to reassign the output again because we're updating the metadata of that object. And it's going to generate three files, an ODE function, a MATLAB object, which corresponds to this system, and then a simulation script here. The simulation script is kind of just a quick way to run a simulation. It'll set up the initial conditions, the boundary conditions, and provide all the descriptions of those as a comment. The other option here is you can run a Simulink simulation. There's a library block for that. And the main input here is taking that workspace object name, inputting it, and it'll fill out the states, inputs, disturbances, and parameters. If there are initial conditions assigned to this, you can pull them in by using this checkbox or just assigning them here. For more information From a quick start perspective, we want you to reference the README on the GitHub page for a more detailed guide. There's also a wiki. Again, the QR code's there for those of you that are interested. And the last thing I want to end on is some future capability. So right now we can parameterize our models with scalars and lookup functions. We want to be able to use MATLAB neural networks to parameterize our models and also build in some of the more control-oriented functionality, such as being able to auto-generate an MPC control law formulation, model or reduction, as well as discretizing our linearized models and converting dynamic to algebraic states. There's some usability on the Simulink side, automating the port labeling. And with that, I think we have time for a few questions.
But is there any questions that folks would have? For component models, are you using existing component models or are you creating new?
So there's a lot. I can answer that. There's a lot of component models in the literature that are being referenced and being pulled into the toolbox.
Timescale control. Just image of the hierarchical. And I'm just wondering, like, is there any problems you feel trying to develop maximally non-effect and you are just doing all layers bottom from top to bottom and with which is the bottom layer is there fastest scale like company problems and trying to mean towards your non-timescale goals. Yeah, so just in the context of higher control facilities, energy systems, multi-timescale is one of the main challenges. That's where higher control has to get fixed, right? Aligning the update rates of each control each level with the various timescales. So from that regard, matching controllers with timescales is something handled by the architecture. But I think the main challenge is how do you achieve coordination between controllers of different functions. Right. So when we first started, we were just doing standard kind of reference tracking. You would design some optimal trajectory over a long horizon of an upload controller and then pass that down to be tracked by lower control. But that's not always the best operation of your system. Sometimes you want to use the fast dynamics of your system to improve operation instead of just being robust to those fast dynamics. So reference tracking really just means ignoring those fast dynamics or being robust to them. So then we are figuring out different ways of achieving coordination and how those ways of coordination can be used to guarantee stability and state satisfaction. So that's one aspect of it. But we've also seen in all these aircraft examples, you really do need to optimize over a long period of time to maximize performance because you have some of these conserved quantities. The fuel within your aircraft is monotonically decreasing over time, and fuel can be used for thermal management. And so you have to basically predict over emission and be able to fully optimize. And things that you do early on in the mission, you kind of feel like shooting yourself in the foot, and you can really limit the capability of your system and you operate the system poorly in the beginning. And so that's where we really think you get optimize over multiple time scales to achieve maximum performance and efficiency.
Yeah, I was going to ask, tool, in presentation, the tool is, I understand, a work in progress. Is there any ability for people to take the tool from your GitHub and then add components that are not currently encoded? Like, how difficult is that to do as it stands?
So in terms of like the single state vertex representation, that capability is there. So you can create component models by defining. I didn't get into the detail here, but there are, it's several slides back, but the edges and vertices are also classes. They're just a generalized structure of what an edge is and what a vertex is. And on the GitHub page, under the wiki, it tells you how to build a component model.
So not necessarily limited to the existing or
no.
Kind of that's what you want. That's like you just stole my last one.
Please play with it. Play with it, but also make sure you don't resource.
Something that I wanted to add, to go on sort of application of this, you know, there, I think Herschel mentioned earlier on that obviously there's a lot of data-driven modeling approaches that folks want to use for various types of systems. And here we are still building this on physics. And a lot of the design optimization that we've done and then the control cosine stuff that Thermal's done still relies on having a franchise model. These aspects of the model that are franchise because fully data-based, you can't actually say I want to optimize TX in your area. I want to understand how those parameters are actually influencing the dynamics. And so there's a fundamental advantage of this approach is trying to retain some level of information interpretability of the model.
Sorry.
Yeah, just one follow-up question regarding the coordination. If the get large model, is there any issues with the
Yes, no, the opportunity to feature work, especially with fluid transport that has a built-in transport delay. We can build this into the graph so that the energy going out of one system eventually enters another system, but it's some kind of delay. It's not anything, but people in the community are interested in modeling this in systems, so it's certainly really good.
When it comes to controllers, if there are delays, you know what they are. You can actually build that into the model and the prediction of something like MPC. So there's some neat ways to address known delays in controllers. Of course, you have to still be careful about stability. You're essentially like planning for it feedforward, but there's some neat things you can do with MPC delays.
Yeah, so thank you for the tool. That's fine. I want to go back to the second slide. Where they talk about the other modeling tools that are available. And probably for this question to the types, like the bond graphs. They have the figures that have many similarities to what we're doing. So I'm going to put comments why we can use bond graphs to do something.
Yeah, so I told Chris, because the question came up, I was going to point it in. Chris actually teaches bond graphs. So do you mind, Chris?
Yeah, so I mean, you know, maybe unsatisfactory ways, but all we're getting at the end of the day is motivation, right? It's all we're doing. And ultimately, you could build some of the models that we built at bond graphs, so they're going to be exactly the same. I hope that, you know, some of the things that like Justin and Herschel, and Nero talked about, there's some parts of the structure of our graphs that is intuitively apparent that we can use to help build some of these, you know, theoretical things on top of it, which I think is a little bit less apparent in bond graphs. So, you know, I don't know if any of you guys have anything on top of that, but that
The other one that also comes up is port terminal systems. Bond graphs was built to simulate this, and they were built to analyze. The graphs up to analyze this from the structure. What's the next to what? What can I import? You don't have that in the bond graph. So, you know, if your goal is just to represent simulating, we'll understand how to break it down by the analyze how to do design on my system. If it's big or small, that's not what bond graphs are set up. The other one is the point I was from you. I didn't get to see it for them from they're clumsy, though it started. Have you seen one that's not working 10 states? You see one that's not working 5 states? They're pretty clumsy to use, whereas these are pretty fast. Couple of mistakes. So, what's something you can talk about is like you talking about that outbreak or dynamic based on it's that having some flexibility on it. So from the most practical perspective, it's the system differential equations, also algebra for the problem statistics. Like that's the fundamental way. Yes, yes, and what's nice is again, sorry, you can take a look and make, if you were just writing out the equations straight up, okay, you would write them all out and then try and figure out, well, which one's your algebraic, which is the differential, they both have the parameters in here. Here, I can take a look at the past equations and look at the amounts of that figure. Really, that's really fine. I'm just gonna set that to 0 relative to the other ones that I have and figure out what I'm gonna take out the rate. As a matter of fact, I can have parts in my system. Okay, or this one's relatively coupled to this other part of the system. And in that decoupled piece, I'm gonna make this piece algebraic, this piece IN. And this part of the system, I'm gonna do something different. Look at they don't really have. Right? If I do a net with that, you know, relatively high. That's really hard to do for you right now, the equations. Thank you.
Okay, I'll wrap up. Thanks. And as I said, the takeaway is please use this and let us know how it's working. But before I get to that, hopefully we've given you a little bit of an overview of these are sort of a really useful tool to have in Designer's Toolbox, particularly as a designer. Again, data-driven systems and database controls is really, really useful if you have a system to take the data on. If you're trying to determine how to do a design for an electric vehicle, you don't have the system already, there's nothing to really take the data on to do the, and I'm making trade-offs now as to whether I have a smaller motor, bigger battery. It's really hard to do a database approach to that, much less what Nero was saying. If you can't parameterize it, you can't really design, right? Fundamentally, they're based on conservation laws. They're less useful to model things that don't obey conservation, like communication protocols and stuff like that, TCP/IP, fine. We will do that much, but for what they're useful for, it turns out there's a lot of physical things that obey conservation laws. It's very useful for systems that span multiple domains. Okay? What's really interesting sometimes is when you write down all of the equations you can do. If you were to go ahead and do the passivity from the input to output that you're talking about, it might be that the choice of output you use is not the same physical characteristic as the input. Whereas if you were using these, right, you might say, well, I'm going to go electrical to electrical passivity. I never think about going electrical to thermal passivity, right? But this gives you the ability to span those types of domains relatively easily. This has already been said. You can understand structural topology. This is what separates it from bond graphs and the compartmentalization. The rest has already been gone over, so hopefully you can see it. What we've shown here, it's been the result of a bunch of different researchers over the last, and when they said 10 years, it was actually a little bit, yeah, I didn't realize it'd been 10 years. Holy crap. And you saw a bunch of different examples, right? You saw sort of aircraft, you saw cars. We've done ships. We tend to go a lot with, we started off a lot with things that were mobile. But as Donald showed you, you can do things that are stationary as well too. It turns out it's very flexible, which is great. We didn't show you as much the validation piece, but most of the models that we've shown here have been validated some way, shape, or form on some type of physical platform. So they kind of sort of work. We're pretty confident that they're able to represent the physics very well. Now, to your point, please take the QR code, go play with it, come up with your own component models, upload them. Let us know what worked. This thing is going to work really well. Is there anybody from the MathWorks in here? Okay, so this is going to be awesome. Like if this turns into like a community thing that everybody's able to use before MATLAB comes along and just buys it up and says, no, it's proprietary. So we'd much rather have it be something for the community to use. And I hope really that there's nobody from the MathWorks in here. Because it's one of those things, it's got a network effect to it, no pun intended on the graph, is that the more people that start to use it, I think the more people will want to use it, right? And if I can go pull somebody else's parameterized battery pack model and I have to develop my own, great. Okay. There's a lot more that needs to be done, even though there's a lot. And what we did in this is just, this is a smattering, a handful of different things that you could do, but by no means is it exhaustive. All of the vertices, they're linear, basic like integrators. What happens if you had a system that had sort of nonlinear differential equations? So it's like nonlinear integrators. Trying to go ahead and augment some of these data-driven, particularly, let's say, on the edges. Right? We've used some of the edges where we've had to use maps and tables sometimes to determine flow of power. Is there a way to go ahead and be even more sophisticated than what we've done in the past? Would love to see larger scale demonstrations. So if there's anybody in there from industry, I'm looking at you, Kingsley. The idea of trying this out on some type of physical system in the co-design area, just again for further demonstration and validation of what worked. There was somebody that was on the paper, Phil. He wasn't able to come, but he did a really nice study on UAVs where he was able to go ahead and use the co-design to show like cost per, it was $1 per hour of flight, and optimize UAV system on that using the graphs. That was pretty neat, right? So you could actually show from a given set of components, what's the way I would put them together to get the best dollar per unit hour of flight time. It would be great to see a couple of other folks in the industry go ahead and try and play with stuff like that, and just, if they can, tell us what they learned. And I'm sure there are other things that y'all could think of that go well beyond this. I will just leave you that, we first thank you very much for coming. That's great. We do hope that you'll take this and run with it a little bit. Nothing could make us happier. And with that, I'd like to say thanks for attending. And yeah, we'll stick around for a little bit. If you have any other questions, if you want to do it sort of pairwise, happy to do that as well too. Thank you.